Next, we see some examples or problems on the definition of the group. Read the problem 1. Show that the set G is equal to set of all matrices 2 by 2 matrices having same element A in all the 4 places, and A is not equal to 0, A is a real number, is a group with respect to multiplication of matrices. Is it abelian? Here we are taking a set G, set of all 2 by 2 matrices, where there is a single element A in all the 4 places, and A is non-zero element, A is a real number. But to show that this set G is a group with respect to multiplication of matrices, and a tag is here, is it abelian? So we go to the formal procedure. I will denote this matrix with A as capital A suffix small a. And here it is, I am taking a B in all the 4 places, and I denote this by capital A suffix small b. I am taking AA and AB in the set G. We go to the multiplication of the matrices. AA is multiplied with AB is equal to, I will write matrix AA and BB BB. On multiplication of matrices, we see we get 2AB, 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 2AB. Here I will write this matrix as A, 2AB. The above, if there is an element A in the matrix in all the 4 places, is denoted by A, capital A suffix small a. Here in all the 4 places there is a number 2AB in all the 4 places, so I will denote this by capital A suffix 2AB. And this is also a 2 by 2 matrix, and here 2AB is non-zero element and 2AB is a real number, so this matrix belongs to set G. Since 2 is non-zero, A is non-zero, B is non-zero, 2AB is non-zero element, and this is a 2 by 2 matrix, and 2AB is a real number, so this matrix belongs to set G. So closure property is verified in this set G with respect to multiplication of matrices. Next we go to the associative law. Let us take any 3 elements in the set G. I will write AA, AB, AC belong to G. And I am taking left side of the associative law, bracket AA, AB multiplied with AC is equal to, in the first property I have seen this can be written as A to AB and this is AC. Again multiplying these two matrices as in the above closure property, we get A 4 bracket ABC. I will write this as A4ABC. And on the right side part I am taking ABAC and this is AA. AA is multiplied with this product. So I will write this is as same AA, and this as in the closure property we can write A2BC. Again multiplying these two we get A2BC, and I will write this as A4ABC. These two are equal, hence these two are equal. Therefore I will write bracket AAAB into AC is equal to AA into bracket ABAC. Therefore, we say that multiplication of elements of these associative. So, next we go to the identity element. Just as an observation, we can find the identity element. Here, what is identity element? In the closure property by observation, if AA is multiplied with some element, we have to get AA. So, by observation, if we replace this B by 1 by 2, we get capital A suffix small a. So I will take here, let AA belong to G and take A 1 by 2 belong to G. Here 1 by 2 is a real number and 1 by 2 is a non-zero number. So this matrix belongs to G. So I am taking this A 1 by 2. On multiplication, AA into A1 by 2 gives, as in closure property, we can write A 2A 1 by 2. Here 2 is cancelled, we get capital A suffix small a. And other way, A1 by 2 into AA gives A2 1 by 2A, and this gives A. So by multiplying A1 by 2 on the right side of AA and on the left side of AA, we get the same AA. So we write, therefore A1 by 2 is the identity element of G. Again, by observation, we can guess the inverse element of AA. Let AA belong to G. Take A1 by 4A belong to G. Then by multiplying A1 by 4A gives A 2A 1 by 4A. Here A is cancelled, 2 is cancelled. We get A suffix 1 by 2. And in the left side also, A 1 by 4A into AA gives A 2 1 by 4AA. Here A is cancelled and 1 2 is cancelled. So we get A suffix 1 by 2. When A 1 by 4A is multiplied with A from right side or from left side, we get the same A 1 by 2, and A 1 by 2 is the identity element in the G. So we write A 1 by 4A is the inverse of AA. So thus inverse element exists for all the elements of A, because here we are taking AA. Let AA belong to that, means A is any element of G. Thus, inverse element exists for each element of G. Hence, we say all the postulates of the definition of group satisfied. Therefore, hence G is a group with respect to multiplication of matrices. In the problem, there is a tag. Is it abelian? So, let take any two elements AA, AB belong to G. Then AA into AB gives A 2AB. And here we are taking 2A and B are real numbers. So in the real numbers, multiplication of real numbers is commutative. So we can write this as A 2BA, and again this can be written as AB into AA. Thus AA into AB is equal to AB into AA. Therefore commutative holds good. Here I will write, thus multiplication of maths is commutative in G. In the above, we have verified 4 postulates, and here 5th postulate is also verified. Therefore, we say that G dot is a commutative group. So this is one important example in the point of examination also. Here we have to note that in general, multiplication of matrices is not commutative. In the lower classes, we have learned that in general, multiplication of matrices is not commutative. But in this problem, we have seen that multiplication of matrices is commutative. Thus, this is one important problem. Next, we go to some other problem. The set Q plus of all positive rational numbers forms an abelian group under the composition defined by circle such that A circle B is equal to A into B by 3 for all AB belong to Q plus. This I am taking positive rational numbers, and the set is denoted by Q plus. I am defining a binary operation on Q plus by A circle B is equal to product AB by 3 for all the elements of Q. So we have to verify all the postulates of the group, abelian group. Here it is asked in the question. We have to show that Q plus is an abelian group. So property 1. Let A comma B belong to Q plus, then A circle B is equal to product AB by 3 belong to Q plus, because this is of the form P by Q, that is the general form of rational number. So this is a rational number. And since A is positive, B is positive, product AB is also positive, 3 is positive. So this is a positive rational number. So this number belongs to Q plus. That means A circle B belongs to Q plus. When A and B are operated, the result also belongs to Q plus. Therefore, closure property satisfied. Therefore, Q plus is closed with respect to the binary operation circle. Next, we go to the associative law. For this, I will take three elements. Let A, B, C belong to Q plus. First part, bracket A circle B circle C is equal to, I will write A, B by 3 circle C. Next, operating these two elements, we get bracket A, B, C by 9. Now, I will write this as A, B, C by 9 because all these are rational numbers and rational numbers are commutative and associative. So, we can write this as A, B, C by 9. And on the right side part, A circle, B circle, C is equal to A circle, BC by 3 is equal to A bracket BC by 9. And this gives, I will write ABC by 9. These two are equal. Therefore, these two are equal. Therefore, I will say associative law holds good. I will add, therefore, circle is associative in the set Q plus. Next, we go to the identity element. In the definition of the binary operation or from the closure property, we can guess the identity element. If A circle B is equal to same A, then B is called identity element. So, if we write in replace B by 3, 3 is cancelled, so we get A here. So, here I will write let A belongs to Q plus, also 3 belongs to Q plus. 3 is a rational number, 3 is a positive rational number. Then A circle 3 is equal to A3 by 3 is equal to 3 is cancelled A, and 3 circle A is equal to 3A by 3. Here 3 is cancelled, the result is A. Thus, 3 is operated with A from right side and from left side, we get the same A. Therefore, 3 is the identity element in Q plus. Next, inverse. Let A belongs to Q plus, we guess the inverse element from the closure property. If A is a positive rational number, then 9 by A is also a positive rational number. So, I am taking 9 by A from the set Q plus. Operating with A circle 9 by A is equal to A into 9 by A by 3, and this gives 3. And 9 by A circle A is equal to 9 by A into A by 3. Here A is cancelled and 1 3 is cancelled, we get 3. Thus, when 9 by A is operated with A from right side and from left side, we get 3 identity element. So, I will write, I can say 9 by A is the inverse of A in Q plus. Therefore, 9 by A is the inverse of A in Q plus. Here I am taking let A belongs to Q plus. That means A is any element in the set Q plus. And 9 by A is the inverse of A. Therefore, for every element in Q plus, inverse element exists. Inverse element exists for each element of Q plus. So, 4 properties are verified here. But in the problem, it is asked to show that it is an abelian group. So, we go to the 5th point. Let AB belongs to Q plus, then A circle B is equal to A into B by 3. Here AB are rational numbers and multiplication of rational numbers is a commutative. We know that in the lower classes. So, I will write AB is equal to BA. And BA by 3 can be written as B circle A. Thus, A circle B is equal to B circle A. This is known as commutative law. Commutative law is verified here. Therefore, commutative law holds good in Q plus with respect to binary operation circle. So, all the 5 postulates of abelian group are verified and satisfied for the elements of the Q plus. Therefore, Q plus comma circle is an abelian group, or we can say other way is called commutative group.